Hey guys, this is a new series that I'm gonna try out. I'm gonna see if it works out. I haven't been very big on the whole series thing. Every time I tried it, it hasn't worked out. But this I'm really dedicated to because I gotta tell you, I like calculus, and you know what? There's no one better to teach you this than someone who actually likes calculus. So first, I suppose I should talk about what this will be about. This is I guess if you're in calculus right now, this could be kind of like a supplement. And if you, it could also just be something you might want to learn. So I'm going to go over basically how calculus works, what it is, and how to use it. And basically, this is my own interpretation of calculus, how it works, and based off of the works of other people that I've read. So, how about we get started? We're going to start out with some misconceptions about calculus. And first misconception to be had is that calculus is too hard to learn. Here, I'm going to just decrease my brush size a little bit so you can actually read what I'm writing. Calculus is too hard. Well, got to tell you right now that that is absolutely incorrect. Calculus is easy. It's easy. Smiley face. All right. So, where calculus gets its bad reputation is that the calculus problems are difficult, but that doesn't mean calculus is hard. I mean, you have difficult multiplication problems, you have difficult trigonometry problems. You have difficult calculus problems too. It just requires you to think in a different way. But the math involved is dead simple. Okay, another misconception is that calculus only has math and science uses. This isn't quite so much a misconception as it is. Let's see, there's something going on with the brush. It's not as bright as I think it. Well, it's fine. You could read what I'm saying. Okay, so the second misconception is that calc only has math and science uses. This is sort of right, I guess, if you consider economics or statistics a math and science. So economics deals with numbers a lot. That's true. There is a math kind of involvement with economics, but the overarching theme of rates, different changes in income flow, for example, that could be applied with calculus and interest, calculated interest. So it does have a real world application. It's not just for calculating trajectories or something like that. And the third one is calculus is for nerds. This isn't right at all, because if you want to go to college and get some sort of degree that isn't like an artistic degree of fine arts or something like that, you're probably going to have to take calculus at some point. So if 90% of the people who go to college are nerds, then yes, I suppose this applies. But really, other than that, most of the people will need to take calculus at some point in their life. So it is required generally for most people. So if most people aren't nerds, then this doesn't apply. So now I'm going to get into how we will think about variables in this course. Generally, we think of a variable as some sort of box. Think of it as like, well, you know Schrodinger's cat. You don't know, there's a cat inside a box, and you don't know whether it's dead or alive until you open the box. Well, variables are like the same thing. You got an equation, and you don't know what the answer to a variable is. Like 8 equals 4x squared minus 4. You don't know what the equation is. You don't know what the value of x is until you solve the equation. Basically, that's the traditional way of thinking about it. So I'm gonna just cloud this right here. Traditional. Or that might be what you generally think of it as. And here, in this kind of course, I want to say, it's not really a course, but in calculus, it's more useful to think of variables as representing functions. Now, generally know what a function is. I mean, you're used to the notation yourself. If you ever plotted a line, you got y equals, let's say, 4x plus 2. And that would actually look something like this. Except in front here, I gotta change my layers. Oh geez, never mind about that. Okay, so this is supposed to be in front right there. I don't know what's going on there and why it's not painting over. There, just pretend that it's painting over. This is 4x plus 2 right there, and it goes on forever in both directions. So this y is actually holding this function. These two statements right here are equivalent, and you could, every time you see y in another expression that say you want to solve a system for, you can plug in 4x plus 2. You're already used to doing that. Well, just think of all variables like this, even variables that are constant. X equals 2, for instance, or y equals 2. We'll go with this. This is a constant expression. This is a variable solved. This also could represent this function right here, which is a straight line across like that. So all variables in this course are going to be functions. Just think about them like that. And even functions like this right here, they can be thought of as a bunch of functions added together. They could be the function 4x added to the function 2. It may not be the easiest thing to wrap your head around, but if you get this, then you're well on your way to getting the rest of the course. So let's talk about notation just for a second now. In calculus, you are dealing with infinitesimally small pieces. Now, don't get me wrong, infinity is a very hard thing to wrap your head around. And the notation that we use to denote this would be something like dx. And this just means an infinitesimally, I'm not going to try and spell that out, so infinitesimally small change in the function x. Because remember, this is a variable and we're thinking about variables as functions right now. So this is an infinitesimally small change in the function x. And where actually this comes from is delta x. Delta x means change in x, change in the value of x. And since this is a Greek symbol, when the inventors of calculus went to make their own symbols, they decided to Latinize it and use the letter D instead of delta. So that's where that comes from. And just to kind of wrap your head around it, I'm going to do a little thought experiment. Dx is infinitesimally small, and it's very hard to think about infinitesimally small pieces. So let's say you have the number 2, and we'll add some value dx. Now, what's this going to equal? Well, remember, this is infinitesimally small. This is much smaller than any number you can give me. And by small, I mean small in magnitude. It's not negative infinity. This is small as in incredibly close to 0. Well, what is this expression equal? It's actually exactly equal to 2. Now but you may be wondering, hey Joe, you're adding something here. This is actually a little bit larger than 2, and well, for some purposes you may be right, yeah. But if you just have this expression right here with nothing else, it's equal to 2. I'll get into some expression where it might not exactly be 2. Just hang on. I might do that in a different series, but for right now, just consider this. It's infinitesimally small, which means it has pretty much no value. Okay, so What I should also say is that this is variable. It can change. Now, that might just have blown your mind right there, because at the same time it has zero value pretty much. Like it's not zero, but it's as close to zero as you can get. And it's also variable, meaning it can change value. Well, how is that even possible? That doesn't make any sense, right? Well, here, let's just draw a line right here. This will be the number line. And right here we'll have 0. And right here we'll have some really low number. Low as you can think of. Let's say like 1 times 10 to the negative billion. This is 1 with, like, this is 999,999,999 zeros and then a 1. So this is incredibly small value. D of x would still be like infinitesimally close right here. This would be d of x. It's actually right next to 0. It's like right here next to 0. But for my purposes, I'm saying this is infinitesimally close to 0. The reason why I didn't put it right next to 0 is because with numbers, you can't have a number right next to each other. Every single number is infinitely divisible. Like if you keep on having something, then you keep on, like, oh, 1/2 of 1/2, that's 1/4. Half of that, oh, 1/8. And you keep on going, and then you keep on going, and then you get like 1/2 to the 1,000th, right? And you could keep on going after that, even though the values get smaller and smaller and closer to 0. You'll never actually reach 0, and you go on an even if you go on an infinite amount of times, you'll never reach 0. You'll always just be slightly above. And you can continue doing that as far as you can go. It will never reach 0. And this basically means that you could infinitely divide any region. So you can't have a number right next to 0, because you could always go like 1/2 of the way in between. And we'll just call like this area dy right here. This can be dy, or right here this can be like df. So basically you could have really, these are variable, but they're all infinitely close to 0. This is an incredibly hard, difficult, crazy thing to wrap your mind around, that all of these are essentially 0, even though they're all different values and they're all infinitely close to 0. But just try hard. I should even like draw a break in the graph right here, because this isn't even representative now that I have this df right all the way far away. So this is a break in the graph signifying, oh, we got super close to 0. This is like infinitely close realm, even though infinitely close would be even closer. I'm sorry, I'm contradicting myself. I'm probably confusing you. I'm just saying this diagram isn't completely accurate, but I think it gets the point across that dx is infinitely close to 0. This is a super low number, and you can get even closer to 0. But you could even get closer to 0 than infinitely close to 0. Jeez, I'm confusing myself with this statement. Just kind of roll with it, okay? It will make sense if you just roll with this one concept. So, what is calculus? Well, there's 2 types. And this is going to be the crux of the course right here. And calculus right here is handling infinitely small values. Infinitely small values. Now, if we go back up here to this thing right here, I said 2 plus dx is equal to 2. That's because dx is infinitely close to 0 and doesn't have, I want to say a tangible value, and that could work well. It doesn't have a tangible value. So how could we handle something that doesn't have a tangible value? Well, as we saw right here, they could vary very close to zero. You could have something incredibly different. So here, let's say you divide a small number by another small number. The smallness of the number will cancel out. Like, let's say you have 1 times 10 to the negative 50 divided by 7 times 10 to the negative 50. These are both very small numbers, but because they are both pretty much of the same magnitude, the 10s to the minus 50s will cancel out and you'll get 1 over 7. Well, in the same way, you can take infinitely small values, say dy, which is a small change in the function y, and divide it by a small change in the function x, and you'll get a tangible value. Tangible value. Which is pretty neat. So this is basically what differentiating is. It's taking an infinitely small value, dividing it by another infinitely small value, and getting a real value. Not real, but not infinitely small or not infinitely large. And then we also have an integral right here, which is kind of different. It's basically adding together a whole bunch of infinitely small values an infinite amount of times, and the notation is used with this, and you're adding from a certain range, so let's say 0 to pi of some function. We'll just do sine, for example, and then you multiply that function by the infinitely small value. So this function right here, sine of x dx, is infinitely small piece by piece. So for each value of x that you choose, this is going to be infinitely small, but this weird looking s thing right here, which is called the integral sign, this means that you're adding an infinite amount of them together. So when you add an infinite amount of infinitely small values together, it's kind of like multiplying it by infinity, some form of infinity. So it kind of cancels out because you're doing it in an infinite amount of time. So this also equals a tangible value. And starting with the next video, I will get into differentials. So I hope this has cleared something up, or at least made you look at calculus in a different light. And I'm running way over time, so I'm just gonna stop it right here. Thanks for watching.